Hi, Doctor. I will be presenting on the building integrated design with a focus on Agriculture Learning Community Center in Kota Tinggi. I will be starting with a brief intro of my project. This thesis proposed an agriculture learning community center which designed to promote environmental literacy, urban agriculture, and social resilience. This project used vertical farming as educational architecture, where the architectural learning community center is a seven-story facilities in Kota Tinggi, which designed to address the food security and climate resilience through an agro-educational for local children. And it applies passive and technology-driven design, where the building incorporates vertical farming, rainwater harvesting, daylight optimization, and natural ventilation for all integrated through a passive design and prefabricated system. And I will be using the building system integration as a framework where the project is analyzed through the building system integration ball diagram, which organize on how structure, envelope, interior, and the mechanical system function in harmony. From structure-wise, this building using reinforced concrete slab and columns as the main building structure. Like it used a 150 thick reinforced concrete floor set with a vertical column which support all the superimposed system and vertical loads, and the support for the envelope and farming systems where the structural components anchor the secondary system like galvanized louver, curtain walls, and farming decks to ensure the spatial openness while distributing the mechanical loads. The building envelope choose for this project is galvanized steel louver with the climbing plant, where the envelope used the vertical steel louvers that attach to an aluminum steel substructure. This is to provide shading, thermal control, and structural support for vegetation. And the envelope is ventilated biophilic facade system, where this system creates a breathable building skin that allow for passive cooling, natural lighting, and integration of living greenery into the facades. And the curtain wall also incorporate with the daylight strategy, where the double glazed curtain wall portions are oriented to maximize the daylight, enhancing the indoor comfort while reducing the energy demands for the artificial lighting. The interior design of the building was focused on the sensory experience and flexibility of the building, where the rise floor and learning deck in the interior space were raised floor to conceal the irrigation and the electrical conduit, where the superimposed farming decks enable the flexible space programming. And natural materials and breathable layout was applied as the material and the finishes are chosen for the tactile comfort and to foster a breathable and adaptive environment to suit the educational and farming, and at the same time to enhance the visual and physical connection to the nature. And from the mechanical aspects, the vertical farming system and the climbing plant system uses the closed-loop hydroponic system where the rainwater is collected, filtered, and pumped via the 75 concealed pipes to the hydroponic rack and planter boxes using the hidden mechanical pump as shown in the drawing. And the integrated drainage and water will be reused, where the draining curbs and embedded pipes remove excessive water efficiently, supporting a sustainable and low maintenance irrigation cycle as shown in the detailed drawing. This is the BSI ball diagram for my building, which it used a four system integration, which combining the structure, envelope, interior, and the mechanical of the whole building system. Together with this system are physically and functionally linked through the BSI model and to improve the environmental performance, user comfort, and the long-term adaptability. This diagram illustrates how the structure, envelope, interior, and mechanical system work together as one integrated framework where these systems are not isolated. Instead, each element is physically and functionally linked to improve the building environmental and spatial performance, where this cross-integrated coordination enhance the thermal comfort, natural ventilation, daylight access, and the user experience while minimizing the resource consumption. And it also enables the synergic design approach where the every system enhance the performance of the other to create a sustainable and adaptable architectural solution. And this is some example of the systems in the BSI ball diagram where, like for example, the number one, which is like the structure plus the envelope, where the steel louvers, which is B, and the curtain wall C's, are directed fixed together to the RC slab A, which to ensure the structural stability of the facade while supporting the vertical greenery and passive daylight design. And another example was structure plus mechanical, where The routing can be done concealed and efficient distribution of the load can be done. And for the purple color where the vertical farming rack and the rice floor system was supported by the RC structure, and this ensure the stabilities that allowed the mechanical and electrical system to be integrated beneath the interior surface. The next one is the mechanical plaster envelope, where the green louvers and the irrigated planter box demonstrate the mesh integration where the water supply, drainage, and planting media are embedded within the facade elements, supporting the sustainability and biofilm. And the curtain wall also directly affect the interior thermal and the daylight condition, influencing the both comfort and plant growth within the vertical farming rack. And for the last one, the pump and the pipe work deliver water to both farming deck and the planter system with all the routing concealed beneath the rice floor system to enhance the cleanness and the safety of the user. The impact of building integrated design on the air quality to meet the human needs. From the psychological needs, the integration of vegetation and vertical farming significantly improved the indoor qualities and by increasing the oxygen concentration, regulating humidity and filter out the pollutants and allergens. This creates a healthier respiratory environment, particularly important in a learning and enclosed space. And in terms of psychological needs, the presence of greeneries offer the multisensory stimulation through scent, texture, and colors, which promotes the relaxation, concentration, and emotional well-being. In terms of sociological needs, the green walls and open farming space support the intergenerational learning and social engagement, where the user can interact with the farming system, building environmental awareness and strengthening the community participation. From the perspective of the economical needs, the natural air purification through the vegetation reduce the reliance on the mechanical ventilation system, where the integrated irrigation and the drainage system minimize the water waste and lower the operational costs, contributing to the long-term building sustainability. For the impact on thermal quality, from the physiological needs, the thermal comfort is supported by the vertical louvers and the green facade that reduce heat gain, and open air corridor and cross ventilation maintain the moderate indoor temperature, which preventing the heat stress release. The thermally adaptive space allowed the diverse user to engage and share environment comfortably, where the shaded zone and informal transition area provide the inclusive gathering spots throughout the day, which fulfill the sociological needs. And economical needs can be shown by minimizing the mechanical cooling through the stack ventilation, shaded facade, and evaporative cooling. The design reduces the energy use. This lower the peak loads and utility costs that make it more cost effective for the community-based program. The impact on building integrity where the structural performance and adaptability. The robustness is ensured with the reinforced concrete slab and detailed structural connection where the system withstand normal use and extreme event like heavy wind or floods, protecting user physically, which fulfill the physiological needs of the user. And from the psychological needs, the visible use of strong materials like concrete and steel enhance the sense of safety and confidence. The clear articulation of the structure and the envelope foster the feelings of order and emotional security. For the sociological needs, the modular reconfigurable structure supports flexible use from classroom to farm areas or emergency shelters. The design promotes ownership and adaptability and strengthening the community ties. From the economical needs, the prefabricated aluminum steel frames and modular panels reduce the construction time and waste. The durable materials lower the long-term maintenance costs and simplify replacement, ensuring the life cycle efficiencies and the public sector affordability. In conclusion, the design showcases how architectural technologies are integrated to meet diverse human needs and environmental challenge, where the galvanized steel vertical louver facade is the key example of the climate responsive design that combining the shading, ventilation, and biophilic benefits. And for the building system, where combining the structure, envelope, interior, mechanical coordinated through the BSI ball diagram, and the integrated approach enhance the building performance, support user comfort, and promotes the long-term sustainability. And the result is a resilient, inclusive, and a future-ready community space that bridge education, agriculture, and architecture. Thank you.